I have some more examples here from chapter 6 on circular motion. So the first one talks about a speed in RPM. So I just want to define what that quantity is and how you use it in these problems. So for number 1, omega is the symbol given to it's called angular frequency, and the units, if it's in the SI units, it would be in rads per second, but often it's also in revolutions per minute, or RPM. Okay, this is not to be confused with regular frequency. So omega is 2 pi f, where f is just called frequency. And the SI units for that would be hertz. And a hertz is a 1 over a second. Okay, so the 2 pi, you can see, is the factor that relates these two quantities. So there are 2 pi radians in 1 revolution. Okay, so we can write the circular motion equations in terms of omega if we like. So the frequency is 1 over the period of any kind of circular motion or any kind of harmonic motion. So t is the period, and that would be in seconds. So that's the amount of time to go through 1 revolution. So if something is undergoing uniform circular motion, the speed is the distance around the circle, 2 pi r, divided by the time it takes to go around the circle. Now I can write that, the 1 over t is frequency, so I can write this as 2 pi f times r, or I can write this as omega r. Okay, so this is linear velocity in meters per second. And then sometimes this is a little bit confusing, but sometimes this is called angular velocity if it's written like this, but it is also an angular frequency. It is the same number. So sometimes this is also called an angular velocity, but it's still in rads per second, so it doesn't matter what you call it there. Where r then is the radius of the circle in meters. Okay, now the funny thing here about, if you look at the units of that equation, that V equals omega r, V is in meters per second, omega is in rads per second, and r is in meters. And you might wonder, well, what happens here when you multiply a meter times a rad? Well, that's the funny thing about rads. They just disappear. It is true that a meter equals a rad times a meter. So that's a little bit of a funny thing about rads. They kind of come and go. Okay, so for this question of the centrifuge, which is rotating at a huge frequency, so this, we're still in question 1. The centrifuge, we're told that the radius that the particles or whatever is going around in the centrifuge travel is 7 centimeters, so that's 0.07 meters. And we're told the centripetal acceleration in there is 125,000 Gs. Now, when you have anything that's Gs, you simply multiply by 9.8 meters per second squared, and that's the acceleration, the centripetal acceleration in meters per second squared. So that is 1.225 times 10 to the 6 meters per second squared. Okay, so Newton's second law for circular motion. Actually, we don't have any forces here, but it is the force that you need to keep that thing going in a circle that causes if it was, say, you're separating a fluid or something, causes the heavier particles to go to the outside of the circle and the lighter ones to the inside. But we're asked here for the angular frequency of the centrifuge. So we have that the centripetal acceleration by definition is v squared over r. And we don't want v, we want omega. So I'm going to write this in terms of omega. We have that v is omega r squared divided by r. One of those r's cancels and we get omega squared r. So that's another way to write the centripetal acceleration in terms of angular frequency. So sometimes that's a handy formula. Now you have to be careful though, that omega has to be in rads per second if you use it in that way. So it's omega that we're after for this question. So let's solve for omega. It'd be a divided by r. So omega would be the square root of a over r. And we have those two numbers right there. So let's actually work this out. 1.225 times 10 to the 6 divided by 0.07 meters. And that gives us an angular frequency of 4 points. This is omega, 183 times 10 to the 3, and that would be rads per second. Now notice here, it's also kind of funny that the meters under the square root cancel. You're left with 1 over seconds. When you take a square root of that, you get 1 over second squared. You take a square root, you get 1 over second. But once again, these rads, they kind of come and go as you need them. That is omega, and that is in rads per second. Now, if we want RPM, so how do we go from rads per second to RPM? We know that, let's write this down again. Rads per second. Okay, we need minutes. So we've got 60 seconds per 1 minute. And then we have 1 revolution is 2 pi rads. And so when you multiply all that out, you get 3.99 times 10 to the 4 RPM, which is a huge angular frequency. Okay, so that's an awful lot of work, but that's how you have to go in and out of these quantities. Omega, angular frequency, F, regular frequency in hertz, which we don't usually use for circular motion. We use that more for like sine waves and just harmonic motion, we use hertz. But for circular motion, we more often use omega. And don't say W, it's omega. Okay, let's look at number 2. So question 2 is a car drives straight down towards the bottom of a valley and up the other side on a road whose bottom has a radius of curvature of 115 meters. Okay, so this is the car driving on a curvy road. And I talked about this in the introductory video, but we're interested in the car down here in the valley. So you don't have to go in a complete circle to be in circular motion. The instant that this car encounters a hill, whether they're going up over a hill or down in the valley, it will be going in circular motion. And the radius of that motion is determined by the circle that sort of best fits that part of the road. And this circle will change depending on how the road is shaped. Okay, its speed is this way. The velocity is this way. The radius of the circle is this, r, and we're told here that it's 115 meters. So it's not a very tight turn. That's a pretty gross exaggeration I've done with that giant car in there. And then it says at the bottom, the normal force on the driver is twice his weight, and we're trying to find the speed. Okay, so remember the free body diagram for something going in a circle. If you, let's just draw well, I'm going to draw it as a dot. Here's the car. It has force of gravity on it, and it has a normal force. That's the force of the road pushing up on the car. Now, if those two forces were equal and the car were going to the right, well, the car would continue going to the right because nothing would make it turn. So if it's going to turn up, then the normal force must be bigger than the gravitational force. But it doesn't matter because we always use the same thing. Newton's second law for circular motion always says forces in towards the center minus forces out away from the center of the circle equal mv squared over r. You don't have to worry about plus, minus, left, right, up, down. It's in minus out. So in is the normal, out is the force of gravity, and that would be mv squared over r. We're trying to find this. V is the unknown. Okay, but it says the normal force is twice the weight. Okay, now whether this is the car, a person, any part of the car, doesn't matter. Everything's doing the same thing. So it says that the normal force is 2 times the force of gravity. This is given. So if you were sitting on a bathroom scale, that scale would be twice your mass. So you would feel really heavy as you round that curve. That's quite big. Okay, so let's sub that into the equation here. So we have twice the force of gravity, that's the normal, minus the force of gravity, is mv squared over r. So 2fg minus fg is just fg, which is mg, is mv squared over r. Now notice how we don't even need the mass, it cancels out, and the speed is root gr. This combination root gr comes up quite a bit for all kinds of different situations. So this would be 9.8 meters per second squared times 115 meters for a speed of 34 meters per second. Well, 33.57, rounded to 34 meters per second. Okay, if you multiply that by 3.6, how fast is this person going? That's 122 kilometers per hour, so that's pretty fast. Okay, number 3 says a bucket of mass 2 kilograms is whirled in a vertical circle of radius 1.2 meters. The lowest point of its motion, the tension in the rope supporting the bucket, is 25 newtons. We want to find the speed of the bucket, and then again we want to know how fast you have to twirl it so it doesn't go slack at the top. Okay, so this is like the ball on the string. So ball, string, ball. There's the top and there's the bottom. And we only ever analyze in this course the top and the bottom. There, different things go on as it's moving up, but we're only worried about the top and the bottom. Okay, so we're given the mass, the bucket, 2 kilograms. And we're given the radius of the circle, 1.2 meters. And you know, it's really hard to twirl something at a uniform speed in a vertical circle. You have to do all kinds of crazy things. So it's not all that realistic that it's actually going at the same speed all the way around. Well, that's okay. At the lowest point, it tells us the tension is 25 newtons. So remember, strings only pull. Force of tension is always pulling. Force of gravity is always down. So we're given here, this force of tension is 25 newtons. Now we could just calculate this right away. Fg is mg. So let's just see how these numbers compare. 2 times 9.8 is 19.6 newtons. Now, you would expect this. This would have to be the case, or the thing wouldn't go in a circle, or the string would break. So notice the force of tension in is bigger than the force of gravity out. And the difference between the two is what gives F net, and that's m times a, where a is v squared over r. So the question we're trying to find here is the speed. Okay, so what is speed at the bottom? Okay, so Newton's second law, in minus out equals mv squared over r. It's always the same for all these questions. So in is ft, out is fg, is mv squared over r. Now we may as well just work that out. 25 newtons minus 19.6 newtons. So this is F net. If you want to write this as F net, you certainly can. Okay, so F net would be what? Be 5.4 newtons. Okay, so that's F net. And that would have to equal mv squared over r. So the 5.4 newtons equals mv squared over r. And so v would be the square root of 5.4 times r divided by m. And that would be 5.4 times R is 1.2 divided by M is 2. And that works out to 1.8 meters per second. Okay, so that's the speed of the bucket. Now we're going to assume it's uniform circular motion, so it's the same speed all the way around. Okay, so that was part A. Now part B, assuming same speed. Oh no, hang on. What does it say? It says, how fast must the bucket move at the top so that the rope does not go slack? Okay, we do not assume it's the same speed. Do not assume same speed at top. Okay, so if it were to be going, well, what would happen if it were going at that speed, 1.8? Would it make it around the circle? And how would you know whether it makes it around the circle? We'll do that part. We'll make our own part C for that, but let's see what happens. The question is, how fast does it have to move at the top so the rope doesn't go slack? So let's look what's happening at the top. And this is also the same kind of problem where if you had a bucket full of water and you twirled it in a circle, if you don't twirl the bucket fast enough, the water is going to fall out. If you do twirl it fast enough, the water will stay in the bucket because the bottom of the bucket will actually be pushing down on the water. Okay, so tension always pulls. Gravity always points down. So when we do in minus out equals mv squared over r, these are both in. So we've got the force of gravity plus the force of tension. There is nothing out. Must equal mv squared over r. Oops, I've got ft. ft is one of them, and fg is the other one. Okay, now the deal is that the force of tension will always be there as long as you're going fast enough, as long as this mv squared over r is big enough so that it overcomes, it's bigger than the force of gravity, and there's some left over. If mv squared over r is less than the force of gravity, well, that's impossible. It won't make it in a circle. It'll just kind of come up. It'll come up and it'll just kind of fall like this. It won't actually go all the way around in the circle. So there is a minimum speed you have to twirl this at, otherwise the thing will go slack. And the minimum speed is when ft equals 0. And so it's fg is equal to mv minimum. And I goofed this up. I don't know what I was thinking when I was doing the introductory video. I solved this equation wrong. And I don't know, I left ft or did something crazy. Okay, mv min squared over r. And so mg is mv min squared over r, which means v min, here it is again, root gr. It came from a totally different analysis, but we keep seeing this root gr. Sometimes it's the max speed, sometimes it's the min speed, sometimes, so it's always appearing. But this is the speed you have to twirl that bucket out at, or else it's going to fall out of the circle. And if it had water in it, the water would fall out. Twirl it faster and it's fine. You just have the string has to pull in. Okay, so this min speed, root 9.8 times 1.2, which was the radius of the circle. And it turns out you have to spin at 3.43 meters per second. Well, that's way more than the 1.8 we found in part A. So if we had carried on with the speed, the 1.8 in part A, well, the string would have gone slack. The bucket would not have made it around the circle. Okay, let's carry on to number 4. And this is the roller coaster. Once again, it says what minimum speed must the roller coaster be traveling so that the passengers upside down at the top do not fall out. And it's a different picture but we're going to come to the same conclusion. We're going to get this root GR that keeps appearing. But the source of the forces on the object going in a circle are now different. There's no rope. Now the thing keeping you in the circle is the normal force between the seat and your body. So there's a normal force that way, pushing you in, pushing you in, pushing you in as you come around the top. And then, of course, there's the force of gravity. And so once again, we have the normal plus gravity. They're both in, nothing's out, is mv squared over r. And it is possible for the normal to go to 0. But if you go any slower, you're going to fall out. I suppose that's why they have like seat belts and things on roller coasters in case it slows down. They don't want you to fall out. So V min occurs when Fn equals 0. So once again, we have that Fg is mv min squared over r. And so V min, again, is root GR. Okay, so lots of these questions we did today had root GR. That was just kind of a fluke. Okay, so this is 9.8. But the radius here is much bigger than the bucket. It was 8.6 meters. So you have to go an awful lot faster on that roller coaster so you don't fall out. 9.2 meters per second. Okay, so that's enough for today.